Thanks for coming to the Functional Monthly. This is the second one. And so again, Functional Monthly is the last Tuesday of every month. And so these are my notes because I can't remember to say them. I'm Taylor. I'm one of the organizers, and Brian at the door is one of the other organizers of SFJS. So we're looking for speakers for session 3 and 4. And to give you an idea, session 3 is still going to be a pretty in-depth advanced session, like this one will likely be, and like the first one was. Session 4 is going to be more hopefully for beginners, just into functional programming. So if you'd like to speak about kind of beginner functional stuff, we'd love to have you. And if you just want to come and watch, definitely come to session 4. Stick around after Leo's talk to just chat with everybody. There's only one talk tonight. Grab the beer because I don't want to take it home, and just feel free to chat with people afterwards. We'll probably stay for about another half an hour, 45 minutes after Leo's talk, or until people start to come around. So, and if you want to hear about anything in a future session, so any topics, just send me an email in the meetup group, and I will try to find somebody that knows about that. And Taylor Smith, no problem. So without further ado, Leo.
Thanks. Thanks for putting this on. It's pretty good. So can people in the back hear me? No, they can. Now can people in the back hear me?
No.
How about now?
Yes.
I see head nods. Perfect. Okay, yeah, so hi, I'm Leo. I'm from UC Berkeley, and actually, wait, can people see through me? People can see through me. All right, awesome. Okay, so yeah, I'm Leo from UC Berkeley. I design programming languages, and I actually used to be a schemer maybe 7 or 8 years ago. Kind of relevant to this group, I used to do something called functional reactive programming, and brought that to the web. And so now, has anybody heard of that? I'm kind of curious. Oh, awesome. So if you haven't heard of that and you're interested in functional programming and the web, you should check that out. Okay, so what today I want to talk about is a project I've been working on for the past couple of years called Superconductor. And relevant to this group is it uses somewhere underneath something called attribute grammars to kind of do a lot of the heavy lifting. And using this, we're able to do big data visualization. So, jump in. Okay, so I'm going to talk about kind of 3 levels of things. And if you have any questions at any point, feel free to raise your hand or shout, and let's make it interactive. So the first thing I want to talk about is beautiful data and kind of what we're trying, the end result that we want. And then to achieve that, I'm going to talk about kind of the programming style that we've been working on, and then finally underneath how we're using parallelism within the browser and automatically through language techniques to achieve it. Okay, so the kind of motivation for this project is twofold. The first one is actually mobile performance. So what you're seeing here is an iPhone battery, and if you look in really close, you'll see that it's rated for, what is it? 5.5 watt hours. So after 5.5 running at 5 watts for 1 hour, or for 5 hours at 1 watt, your phone is going to run out of power. And this is about 10x less than what a laptop will be running at. So what this in practice translates to is actually roughly 10x less performance between a phone and a laptop. And so where a lot of this project started was actually trying to get essentially really fast websites running on the phone. Like we speed up web browsers, and so that's a lot of the early work here was actually to browser compiler technology. And actually more recently, we've also been looking at if we do data visualization on the phone. The second half of the motivation, what I'm actually going to be really talking about today is actually just straight up data visualization. Hopefully I don't have to motivate why we want to look at data too much. But what I found interesting is a quote from Tufte's book, which basically says, well-designed graphics are usually the simplest. And the reason I find that interesting is that one natural conclusion from this might be, well, our small and static charts are enough. Like they're very simple and they should be able to communicate what we want. However, I'm looking at the case of big data, and there the scenario is a little different. So instead of trying to report from a chart, we're actually trying to do knowledge discovery. Somehow we have to analyze the chart and pull out information. And so as an example, I'm going to walk through how do we report voter fraud? How do we analyze and understand it? And so what I'm showing you right here, I feel like I'll be your weatherman or something. So what I'm showing back on the x-axis is voter turnout. And so, for example, in the kind of what we're seeing on the right is Sweden is very far on the right on the voter turnout. So most of Sweden turned out. Swedes like to vote. And kind of the y-axis is kind of what percent of the country turned out, how many towns turned out, how that voter turnout. So this chart also communicates another thing, which is for all these democratic nations I'm showing, we kind of have this nice bell curve shape for the turnout. And this is in a lot of natural social processes. You will see this normal curve. And so this is kind of useful because now if I show you another very simple chart, I'm not going to tell you what country it is for various contractual obligations, but it is no longer this nice and smooth bell curve. And so I've communicated that there's probably some sort of fraud going on in this country for this election. For some reason there's a very thick tail on the right. However, now that we, now that we know that there's some fraud going on, we want to start doing data exploration, or knowledge discovery. We want to understand what this fraud is. And for that, I'm going to show you a demo of the system that we built. So this is okay, cool. All right, so what I'm showing you, I'm going to have to share. So what I'm showing you here is a visualization of about 100,000 data points running in the browser. It is zoomed in a lot. And what each one of these data points is from that fraudulent election. And what each one represents is a town that had a voting station. So let's look at a nice one. Okay. So we see this little white square right here. And what that means is, because it's a white square, that means they voted mostly for the opposition party. Well, from a lot of these other points, we see red, which means that town voted more for the incumbent. And the size of the square kind of tells you how many people turned out in that town. And so we start to see some interesting things already, where we zoom out and look at the full country, that we can see that there's a lot of pink. So the vote was somewhere in the middle. This 0% should actually say about 50%. This vote actually was split down the line. The incumbent just won by a hair. But we know there's some sort of fraud going on, because I just showed you that weird curve. So what we want to be able to build with our system is kind of analytic tools. So what I'm going to show, so what you see on the bottom is a little slider where I can control the range of voter turnout to show. So here I'm showing 40 to, let's do 60%. So this is all the towns where the voter turnout is between 40 to 60%. And it's not very, it shows the data, but it's not very intuitive, like what's happening when I move the slider from left to right. And so once we use our system, so here I'm actually just I'm just running a normal JavaScript. Once we use our system and use GPU acceleration, we can do the same thing. So go towns where 40 to 60% of the people turned out. And now we have very nice and smooth, hopefully you noticed, animation. And now we can start kind of actually getting a good feel for the phenomenon. So let's first just recreate that bell curve that I talked about. So let's try to find that bell curve. And the bell curve will show up by the height of the amount of people who voted. So nobody voted in the 0 to 20% range. But as we turn up the voter turnout, we see that most of the country voted in this 45 to 65% range. So actually, I've also taught you this is not Mexico. So this kind of cuts down the choice of countries. But for this to be a bell curve, it has to increase smoothly, and then it has to decrease smoothly. It's decreasing, but then it plateaus. So we have voter fraud. So that's communicating the same thing. But now we can start investigating. So I'm looking at the full data set, and what we start to notice is some weird things. So first of all, let's look at these let's try to understand the towns that voted in this 80 to 100% zone. So first of all, they're mostly red, so that means that somehow the incumbent has these 80 to 100% towns where every single person voted and turned out and voted for them. Then we can zoom back out. Might do something like, okay, let's select those towns and highlight them. So now what we'll see is actually, it's not just the towns, but actually entire districts have these 80 to 100% votes. So it's not just fraud at a local level, but actually at a district level. Now that's actually kind of interesting. This means it's sort of systemic fraud. And then kind of, if we're looking here, let's see what happens when we replace the fraudulent or the suspicious votes with exit poll data. So we're not throwing them out, we're just replacing them with what independent observers thought. Now the vote for the incumbents dropped to 47%. That means they no longer have a majority, and now you can have a coalition among the opposition party take over the country. So I'm not going to tell you what country this was, but that it would have made news. The incumbents.
When was it?
I'm not going to tell you.
Okay, what was that?
Does it begin with an I?
Over beers. So but basically what I'm showing you, I think the really cool thing is that, first of all, we want to have this high performance in the browser, and what we need it for in particular is not just for stuff like zooming in and out. Like that stuff's actually in practice you don't need anything fancy for. But I'm doing this real-time filter. As part of this filter, I'm actually recomputing the layout and re-rendering, and that's where we need to get the performance. And this is where a lot of our technology that I'm going to be showing you has to solve. Okay. And again, feel free to jump in with questions as long as they don't break contractual obligations.
How did you actually accomplish the technology behind the rendering engine here? Is this C3 or?
You're gonna have to sit for the next half hour. So that's what I'm gonna be. I'm gonna show you what's underneath and how that's all the scientific stuff, or part of it. Okay, so so instead of using D3, which actually would be about roughly 50x too slow to do what I just showed you, we actually built a tool, Superconductor, and it's a collection of domain-specific languages for data visualization. So I'm going to unpack that a little bit. So domain-specific languages that are kind of these restricted languages where we make them productive for visualization, and it's to make it good for compilers, we actually made them a collection of them. And so this kind of restricts the scope of each language such that I'll be able to use the techniques I'm about to show. And the second part is that it compiles. It has we're using a compiler, which means that we can target multiple platforms. We can do compiler-level optimization. In particular, we're going to be outputting parallel JavaScript. I've been playing with something called WebCL, which lets you do general computations on a GPU. Something called WebGL, which lets you do rendering on a GPU. And something called WebWorkers, which lets you use multi-core processing. And you can access all of these things through JavaScript now. However, the low levels, so that's why we want a compiler that goes from high-level domain-specific languages down to these low-level systems. And hopefully at the end of the talk, you'll sort of understand exactly what the slide just said. Okay, so like I said, Superconductor is a set of domain-specific languages. I think it can be understood to actually think about trying to do visualization in Excel. So you're going to have to describe your data in some way, like select your data, describe it. Then once you have your data selected, you're going to pick some sort of layout widget, like a bar graph, to describe it. And what do you have to do for a bar graph? Well, you have to laying out the points into a bar graph and then painting all the pixels in the bar graph. And then finally, maybe you don't want to use the stock bar graph, you want to stylize it, you want to change the colors, stuff like that. And so, again, we're going to want a high-level language for talking about each one, and we're going to want to parallelize them. And so what was kind of cool is we realized that we actually can use existing web languages for some of these tasks. Like if we could talk about our data using JSON and talk about styling using selectors. Does everybody know what JSON and CSS selectors are? This is the JS meetup. Great. So probably not as many of you are familiar with attribute grammars, so I will get to that. And that's how that's our new system for dealing with the layout and painting component. And just as an example of the effect of this, JSON is this nice data format, and it's not exciting on its own in terms of performance, but once you're trying to load in like a 50 or 100 megabyte data file in real time, it could easily take 10 seconds, and now it starts becoming an interesting problem, at least from a compiler perspective. To make that visceral, let's take a look. So here I'm just going to use, I'm going to load in a 1,000,000 node data set using the stock browser's JSON parser. We can wait, you can see the CPU at top, it's chugging away. Okay, and then it ran. So I didn't count that, but it's like somewhere in the 5 to 10 second range. Now using the same thing, but we're going to use multi-core JSON parsing using part of some of the framework we built. And I don't know if you want to count internally. Ready, set, go. That's a lot more satisfying. Now we can start talking about streaming from the database. Yeah, thanks. So DSLs are awesome. That's lesson number 1. Okay. Okay, but we're the functional programming group, so we want to talk about attribute grammars. So we're going to be talking about using them for the layout system. And the first thing I want to establish is why we're looking at using a language here. And it's actually not just performance. So building a layout system, like imagine that you're trying to implement a D3 widget or a jQuery widget for a custom layout. Doing it manually is pretty painful. So the background for this work was actually trying to build a CSS engine for a really fast browser. But actually implementing all of the CSS standard was a big deal. So what you're seeing up here was, I think at the Apple website rendering in 2 different browsers, they have slightly different interpretations of CSS. It's hard to actually build a layout widget correctly if you have like 100,000 lines of C++ implementing your layout widget and this 500-page standard. So even getting it manually correct is kind of hard. And then, I don't know about you, I'm not actually very happy with the tooling for CSS. Like, when I have a question about why something is in slightly the wrong place, like I wish the tools would be a little more informative. But when you have this big pile of 100,000 lines of C++, or thousands of lines of jQuery and JavaScript, it's hard to actually, for any sort of tool, to really give you good feedback. And then, likewise, I think I've pounded into you guys performance on talking about parallelism, but also we want to get other features, like we want a low memory footprint if you want to run like Google Glasses. It's actually browser-based. You might want to have incrementalization, so you resize a page, you don't have to recompute everything. And implementing all of these optimizations for every single line of your layout code is not a good time. And so we're going to want our domain-specific language to handle it. So yeah, I guess that's kind of the punchline here, is that instead of manually writing our layout code, we want to manually implementing our layout widgets and our layout engines. We want to write them in our DSL and have the DSL spit out a really optimized and awesome layout engine for us. So in particular, the layout engine, what we want to do is take in your data structure, let's say like a DOM tree or like the JS, like a JSON file. I'm just going to run through our layout engine, for example, that tree map I just showed you, and then I'll spit out the rendering. We don't just want any layout engine, we're going to want a parallel one. So we're going to want somehow inside a lot of WebCL and WebGL web worker code going on. And does anybody know all 3 of those technologies? Vaguely, awesome. So yeah, so not a lot of expertise to go around for that. And so it's nice if we have a high-level language that will compile into it. And so the input will be our attribute grammar. All right, to clarify this a bit, has anybody used Yak or Bison? Does anybody know what Yak or Bison are? Yeah, YACC, yeah, way back. Okay, this is a pretty good showing. It's like almost half the people. So a lot of the technology I'm showing you is actually started back from people trying to write parsers, but we're just going to supercharge it here. The idea is, you're going to want to, like a parser, we want to compute on a tree. Same with the layout engine also computes on a tree. So here you can think of this tree as like a DOM tree. Here we have a root node, a horizontal box, and maybe some leaf nodes near the bottom. And we actually have a more modern form of Yak. Luckily, you do not have to deal with 1970. I think it's created in 1970 alongside of Unix. So
it's in the BSD 4.2 menu.
Yeah, it's a standard distribution. You can get a lot of package managers, but it doesn't have a lot of things though.
What's wrong with louder languages? What's wrong with louder languages?
Excuse me?
What's wrong with louder languages?
That's actually fine for us. We're interested in what happens after the parsing, so I'm not going to even comment on that. Actually, we have a JSON parallel parser, so we're fine. Okay, but basically what things we want to compute on the tree. So for example, I'm going to walk through building an HBox node. So let's say you want to make a horizontal layout widget. So it's kind of simple. Well, we need to kind of get the schema of the tree. So people wrote XML at any point in their life. I'm sorry. So we needed to find the layout, essentially the schema of the tree. So we'll say a horizontal box, just to make this easy, has a left and right child, and just say their nodes. We'll say that the person providing the data to visualize will provide some data. For example, for all the HBox nodes, they'll give the X and Y field. And what our layout engine is going to be responsible for is computing the width and height fields for each node. And to compute them, they're going to actually define constraints. And this is where we start actually our programming. And so in this case, we're going to define the width of a horizontal box just to be the sum of the left and the right node. And so the cool thing is this is actually kind of like CSS, like if you're writing CSS. The first, let me do this backwards. So the first thing is that it's single assignment. Like in CSS, you can't give the same, like 2 different widths to the same thing. One of them will win out over the other. So same thing, so we only define the width once. The other part is that we're actually going a step beyond CSS where we can introduce computation as part of the constraints. So in this case, for the width, we could say the width of an element is the sum of its child widths. And that's actually enough for our layout engine and for our compiler to analyze the dependencies of the program and actually spit out the layout engine. I'm going to walk through one more example of this. So I want to give you guys a feel of kind of how flexible this is. So I just whipped up a small IDE. Okay, here's our HTML that we want to visualize. And I wrote most of the schema before, so we have, for example, an intermediate node and a leaf node. And let's write a simple calculator. So this is one of those canonical attribute grammar tutorials. And so what we'll say is on leaf nodes, we need to find a bit more schema here. We'll say that leaf node has an input value, which is, I don't know, int. And so now we have some leaf nodes. We'll say the first, it's kind of like normal HTML. The first one is value 0, the second one is value 1. Let's do another value 1, another. Copy these. Okay, and then we had, let's write a constraint. So let's double the, we're going to try to generate a layout engine. So now when we generate, that's what the green meant, was we generated the layout engine. Now when I run it, it'll be able to compute on that tree. We're not visualizing anything, but we are able to do computations on the tree as part of the layout process. So to make a calculator, instead of having intermediates do nodes do nothing, let's have them compute something. So we'll say, I don't know, say the results of each node will actually just be the result of the left node. That means we need to have the result for each node. So this is part of the schema. So we'll say the result of the leaf node is going to be, let's undo the doubling, just for fun. I think that's enough. So live demos are always interesting. So, okay. So the result node for leaf node is just taking the double, divide by 2, we get 1. And then for the intermediate node, we're going to say it's the first, the left child will propagate its result. So 0 goes to 0. It's actually identical. I have no idea why that did that. Okay. Anyway, so now to make it a calculator, for example, we might want to say, instead of just intermediate nodes, let's make a plus node. So for the plus node, we'll take left.res and add it to right.res. Now if we go to our XML, let's make this node to be, what do we call it, sum or plus? Plus. Wow, syntax is great. Okay. So, actually this is, so now we should get when I run this, we should get 1 plus 2 is 3, 3 complements. And so you can extrapolate how we can build a full calculator here. So for any type of node, we can build like a plus node or a minus node. Let's just do that for completeness. So minus node will do minus. So here. So 0 minus 1 should be -1 when we run it. So we generate the layout engine. Then we run the layout engine, and we get a -1. Okay, so any questions at this point? So now all of you can write attribute grammars. You can't visualize them yet, but so I'll show the last part there. So if you want to actually visualize something, I'll explain this in a bit. You'll be able to do something like, let's say here for a leaf node, we want to draw a circle. We'll position at 0, 0, top left of the screen, and the radius we'll do as res. And I'm not going to run this, but like that's the basic idea. The kind of cool thing here is that because this is declarative, so functional programming and all that, I can actually change the line ordering of all these things. It doesn't matter. The system still runs. It's constraints, not actions.
Spreadsheet.
Yeah, exactly. So this is data flow, single assignment, actually a very deep connection to spreadsheets. So I want to show kind of this. Using what I just showed you is actually enough to run this thing I'm about to show you. So a fisheye effect, so kind of like in the dock, this guy right here. So here's some tree. I'm going to run. Now the cool thing is that as I move the mouse, we're going to change some attributes and then rerun the layout engine. And then if we actually look at the visualization of what that means with all those paint calls, so this is actually a pretty flexible approach. So to kind of reinforce that, here's like a little gallery of different types of visualizations we're able to make this way. So this is not your mother's parser generator. I'll show you maybe if we have time at the end, this guy right on the bottom right, that weird GPU thing. And then kind of what's fun is on the top right, you're actually working with Mozilla to build a parallel or a multi-core layout engine for the Servo browser. And here's on the top right is a screenshot of actually rendering Wikipedia from using our CSS attribute grammar, which is a multi-core 9-path. I'll explain to you. It's a multi-core layout engine generated by our system. And now we're actually working with Mozilla to build it into the browser. Okay, so I threw this in because I think this is an interesting prep. So the question is, like, what am I drawing upon to achieve this? So in 1967, our man, Newt, started looking at the attribute grammars actually as a way to define the semantics of languages. And so that was pretty cool. But pretty soon on, about, this might be wrong, but I think 3 years later, the AT&T guys built Yak, which is a parser generator as part of Unix, which actually used the same ideas now instead of for semantics to actually get stuff done. That was cool. Then the functional programming guys went ahead in the 80s and said, oh, the people use this stuff. Maybe we should make it really fast and explore that. And so there's kind of this nice ping-ponging between essentially the functional programming guys and the compiler guys. Then the compiler guys, and this is actually a lot happening both in the US and Europe, started looking at, well, can we start making this type of formalism really expressive? Can we make it lazy? Can we do, instead of just these single assignment variables, can we do kind of iterative constraint solvers, stuff like that? Then functional programming guys kind of gave up. They kind of mellowed. They formed this kind of coalition around Miranda, the Haskell, and then now I guess around the Coq. And I guess I forgot what that H, whatever. But they're clung to these kind of central languages, and they're cool languages, but that kind of killed this line of research. But the Europeans kept going, and they started looking, well, instead of parser generators, we build full IDEs, stuff like Eclipse, so that define your language semantics, and bam, you have a full IDE. And this is in the web community, we're actually starting to see similar things. And then about 3 years ago, my group started working on something called program synthesis, where we use stuff like SAT solvers and stuff like that to actually kind of a very different way of building compilers, and different mentality, but that actually let us improve the expressiveness and performance, and a lot of cool stuff, and I'll show you a bit of that later. But that's just kind of I think a fun aside of what's going on with these attribute grammars. Okay, so now that you have a feel for what it means to program a new type of visualization in Superconductor, I want to talk really what's going on. The first thing is the output of the compiler is actually a sequence of tree traversals. So here, for example, I'm showing several copies of the DOM. And for example, if we have a layout engine that's computing with height x and y, it'll do this sequence of tree traversals. So for example, the first pass would be bottom-up, compute all the widths and heights. Once you have all the widths and heights, then you can compute all the x and y attributes for each node. Well, maybe that's the top-down over the tree. Once you have all those, maybe whatever rendering. And it'll figure out, like, look at all the dependencies and figure out that sequence. The kind of cool thing is I'm actually showing you also something called the dependency graph, which shows you kind of the sort of structure necessary to do safe parallelization. So as an example, what this means is for that middle traversal going top down in the tree, you can imagine spawning a new thread at each node. That once you reach that node, you spawn a new process, and it'll actually traverse down its own subtree. And so pretty much as many levels of the tree you have, you can actually exponentially grow the number of logical processes. Of course, this is not how you want to implement the parallelism, but this kind of exposes the parallelism that we need to build a parallel implementation. And what's kind of cool here is, I think, two things. First is, this sequence of tree traversals work no matter what data set you have. So if you change the values in the tree map, you throw in different web pages than Wikipedia, the same sequence of tree traversals will still be correct. They'll still have your page. And then the second part is, and I'm happy to show you afterwards, that the compiler is actually able to reason about these data dependencies, so the language is restricted, and it can actually automatically handle the parallelization for us.
Can you guarantee all your constraints are solvable?
It's essentially we run a scheduler to figure out for each traversal what can we guarantee we'll have all these dependencies met by the time we reach it, and then we'll schedule it for that traversal. And I have a nice little slide after that I can walk you through that, but it's kind of cool.
So what we're seeing here is a pre-processing, compilation.
Yeah, so this is like offline. Like we generally use this offline, so you can think of it as when you're compiling your browser or you're minifying your code. This is happening at the same time. I want to do it on the fly, but that's another story. So what's kind of fun is to actually look at what we generate. So for example, of CSS, we generated a 9-pass tree traversal where it's doing the sequence of top-down, bottom-up traversals. And we actually had, in the multi-core case, we actually could do some fancy types of traversals where we have more complicated dependency patterns. But on a GPU, you can only do, you want to do more restricted things, and so we only do these top-down, bottom-up traversals when we run on a GPU. So that's kind of high level there. So hopefully, when I'm showing you these arrows, I'm starting to make you think in terms of parallel patterns. These arrows going up and down. And when you're doing parallel programming, that's actually really important. And to give one example why, let's say we wrote the CSS specification. In our case, we were targeting the CSS 2.1 standard and trying to write the grammar for that. But actually, by the time we kind of made good progress there, we actually, CSS 3.0 happened, and then 4.0 happened, and actually the standards committee decided to stop giving names to the standards because it just changed so damn fast from the language. And so basically, the issue for us is that we changed the spec a little bit to put in this new feature, but then the schedule changes a lot. And when you're doing performance programming, you actually really care what code and what the structure of this parallel code is. So this was a big issue for us. So our idea is actually we're going to extend this attribute grammar, this basic declarative layer, with a new way of parallel programming where we actually could guide the parallelization. And so it's still going to be declarative, and it's going to be something called behavioral specification. So as an example, I'm showing you on the top the parallel essence of CSS. Don't worry, it's just a bunch of up and down arrows, but that's how you parallelize it. And the thing is, whenever we change the CSS attribute grammar, we don't want that structure to change. So we are actually going to use this not just as an output of the compiler, we're going to actually feed it in as an input. So this is going to be part of our specification. And what this means is, I'm not showing you all the schedule, and actually purposely, that's the formalism. You can punch a hole wherever you're going to trust the compiler to fill it in. So in this case, all these blue underscores, it might be filled in with another traversal, maybe with which attributes to confirm that pass, the structure of the parallels, different things like that. And this is good. For example, I don't really care when one individual attribute gets computed. So for example, if we change the spec and the widths instead of getting computed in the first traversal rather than the fourth, like if the scheduler and compiler moves that's small potatoes. It's just like a little computation, and it's still parallel, so I don't care. But things I do care about is when it breaks that sketch. So for example, if the last two parallel tree traversals is this last pair of bottom up, top down have to get fused together into one sequential traversal. I just broke the parallelization, and that's a bad change to the specification, and that will kill our performance because we just added sequential code. But because we have this spec here, if I hand this off to an intern to do a bug fix, the compiler will refuse this bug fix if it breaks the schedule. So this is actually very important. This gives you a structured way of doing parallel programming. So we found these useful. For example, in that case where we're sharing code, is actually had a freshman at Berkeley writing the CSS spec. Like this enables the share code. It was also helped him test ideas of how to parallelize, like what patterns are possible, and then finally also debugging. So when you had an intuition, what part of it was broken. So this is my claim. This kind of this way of pattern programming is good for parallel. Yeah.
Can you talk a little bit about what partial means and partial behavior? So partial is basically that you have some parallel patterns that have holes that you can fill things in, but it's basically the behavior that's being specified is the traversal of the tree directions, and that pattern sort of is a behavior.
So so you're very close. So the question is, what is partial behavior? And actually, let's step back. So what is full behavior? I claim that what C++, if I ran this through C++ or JavaScript code would generate, that's full behavior. We know at every step what the schedule is. But I don't want to write that. I don't want to feed that as input because that's what I'm trying to get the compiler to do for me. I don't want to fully specify the full imperative nature of the code. And so I just want to specify parts of it. For example, maybe I don't even care about the second half of the schedule. I just care about those first two traversals, and I trust the rest will work. I could say that, and that will be part of the behavioral specification, part of the schedule. And then I'll trust the synthesizer to fill in the rest.
So does this use basic promise patterns to manage, sequencing, or?
So the question is, do we use promises to coordinate this stuff for the pattern? So this is all actually running offline. So we pre-compile the code, and then at runtime we're running on the GPU. So we can't even have a line dead in our code, for example.
Okay.
And then promises are generally dynamically scheduled. For my full feeling on those, check out functional reactive programming. That's my answer to how I feel about promises.
Okay.
I would claim it's a generalization and a synchronous generalization of promises. Does that make sense? Okay. All right, so now the kind of cool thing is, as a performance guide, now that we have these patterns, now we can optimize the heck out of them. So as an example, imagine we have a JSON tree. The question is, how are we going to put that in? How's that going to look like on a GPU? So how are we going to do the traversal on the GPU? The first thing is that you can't just run arbitrary code on the GPU. It really wants nice for loops over arrays. So in this case, for example, instead of doing to do bottom-up traversal, we'll go through the entire level of the tree in parallel, then we'll do another for loop over the next level of the tree and go all the way up. And so you have to start doing these transformations for code when you're dealing on a GPU. So when I ask, has anybody written WebCL or WebGL, this is the type of stuff you want to be thinking about. Our patterns kind of take care of it for you, because we'll spit out this code. The next part of this thing is, well, how does it look like in memory? In JavaScript, you just allocate an object and have some fields in it. You don't worry about it. But in our case, actually, well, if your object has fields, it's going to have to go in its own array. So we'll have an entire array filled just with attributes, an entire array just with X attributes. And if you want to get really good performance on the GPU, this is the type of stuff you have to do.
It's like old Fortran style.
Yes, exactly. Like they made it for performance. Like this, the LBL guys like uphill from me still write Fortran for this very reason. But the cool thing is, because we have the DSL, we can compile it to this formalism for you and get that performance automatically. How are we doing on time? Okay. Yeah, I guess I put it under, so it should be good. All right, so I'm going to show one more example of the type of trickery that we want to use the DSL for getting GPU performance. And so the next one is actually dynamic memory allocation. So actually, has anybody written GPU code? Yes. Can you call malloc on a GPU? No. All right, I'll explain that. So let's say we're doing the bottom-up traversal and we want to paint a circle. Actually, because we're doing this traversal, we're going to want to paint a lot of things. We're going to make lots of circles and shapes. That'll be kind of generally our last traversal of the tree. The issue is that if you look into the code, let's say we're implementing this in JavaScript, that somewhere in the circle code, you say, well, let me create some memory object for putting in the vertices of the circle, because we're going to have to make a vertex for each. It's something called tessellation. And once we have that array, we're going to fill it in. So We're going to allocate an array, put in vertices, and then we'll loop through it, filling in values. So the issue is you can't call the new array while you're on the GPU, so we have to be a little smarter. And again, we're gonna use attribute grammars to fix this. So the first step we're gonna realize is that we're actually gonna split up the computation. So first we're gonna allocate all the memory, then once we have all the memory, then we're gonna use it. So the first pass, we're gonna go bottom up over the tree and just figure out how much data each node needs. And that's the normal constraint stuff I just showed you before. We can compute that. Once we have that, then we'll allocate one big array, and then we'll just give me the big array, and this will be sequential code, but it's essentially one instruction call, so we're fine. But then we'll, now that we have this big array, now we'll traverse through the tree and fill it in parallel. We'll call it the actual, again, we'll run those constraints to fill it in. And so we've just kind of avoided that dynamic memory allocation through the staging. So, any questions on that? This is actually pretty fun, so, okay.
So it sounds like this works only if your tree never changes within a given page.
Yes and no. So it's definitely a functional description where we're given a functional view of the graphics, we're given a tree, we'll output it. We could do things, for example, it's sort of the history of the attribute grammars that one of the reasons it's made was that, let's say one of the attributes changes, the same trick we use to figure out what to parallelize, we can figure out what we need to recompute. It's actually the same history. Like, we haven't done it in our system yet, but that's actually one of the reasons we got drawn with this formalism, is that we essentially have 30 years of that type of compiler to rest on. Okay. That was a good observation. So to kind of unpack that a little bit more, remember I wrote that funny render call while I was in the grammar? So this is kind of our, let's say you want to draw a line, maybe in 3D, so X, Y, Z, and then for the first point, X, Y, Z for another. Maybe you want to draw 2 lines as part of the node, like a review box, as well lines. What this unpacks to is a attribute grammar. So first step, we take the line, we actually do the allocation call, and we compute the size for each one. And this will get scheduled as part of the first traversal. You do see my mouse, okay. So this will get scheduled in the first traversal. And then for the second traversal, we're going to pass down, this all should be in green as well. But basically in the second traversal, think of, for example, the first line. Or actually, no, the second line. The second line will be the same, the buffer position of the first line, but plus the size of the first one that we computed in that first traversal. So we have all the data we need. If you want to step through this, I don't know if I can post the slides somewhere.
So it's basically a stack, right?
Yeah, it's like a statically allocated stack. Yeah. Okay. So that's the basic system. I'm going to just show some kind of examples now to walk through. So the first question is performance. So for that tree map I showed you at the beginning, I wanted to look at a few things. One is just layout, just solving the constraints, and next is rendering. Once you know the size, what goes where, how do we paint it in, and then finally kind of end to end. And what I'm showing here is the layout rendering end to end. And what these two horizontal bars show is about a 40 millisecond deadline for doing animation, so 24 frames per second, and then 100 milliseconds for if you're doing kind of hand-eye interaction. So we want to have the bars below at least one of these lines. So in the case of layout, this black bar, what I'm showing is we just output a naive JavaScript, kind of how if you're going to write some D3 code, what it would look like. And for just the layout of that tree map, it took about 2 seconds. So we're nowhere. This is a log scale plot. We are nowhere near where we need to be. Once we run our compiler, and before we do parallelism or anything, but just we use that funny array representation to kind of turn our code into Fortran. Now we actually hit the at least for layout, this sort of interaction time. So that's cool. And now once we have the Fortran, it's actually not so bad to parallelize it. Just put in parallel for loops, for all 4 loops. And then once we put in parallel for loops, we get another 5x speed up. Now we're actually running on the GPU. And stepping back a bit, so the first jump we get 14x, the second jump 5x, multiplied together, that's a 70x speed up. So attribute grammars. No? It gets better. So we're in the web world, so we have lots of cool APIs. So not only the next one for rendering, for for the version, when we're just doing arrays, we have no way, we just tried to call to canvas to, paint square, paint circle. That did not work. We were again maybe 500 milliseconds or 700 milliseconds for this is for the rendering pass. So that was a problem. But once we used WebGL and WebCL, we actually jumped, 32x. So go web. And then kind of end-to-end, if you calculate it, we're going to have about a 53x speed up, so that can mean on your phone we're 53x faster, but on a laptop you can think of it turn around, that's 53x more data you can visualize in your browser. So either way, it's pretty exciting. For example, if we go from 20,000 data points to 1 million, that's pretty cool. So for the last part, I want to, now that you have the feel for the layout engine, I want to kind of jump back out to how this goes together into a full system. And I see some whisperings, a lot of people recognize this. I'm not going to play the video for it, but what I'm showing you here is a demo that Brendan Ike and a bunch of others at Mozilla did of running Unreal, not old Unreal, but Unreal 3 in the browser at, I think it was somebody saying 200 frames per second, something ridiculous. And they're doing this to talk about this cool project called asm.js, where you can essentially treat JavaScript as a target language, as I've shown you. But I think it's something missing from the message of all these Mozilla talks is actually a lot of the performance isn't from JavaScript, but from parallelism. In particular, in this case, it's actually WebGL. So it's not just fast JavaScript, but we're actually rendering on the GPU, and that's where a lot of the performance comes from. And the significance for the talk, what I've been talking about is, well, WebGL is just one technology, and it's actually pretty limited. I was using WebCL to essentially do these parallel for loops. It's a little more flexible than WebGL. On the CPU side, they also have multi-core that we want to use, and within each core there's something called SIMD instructions, which is actually kind of, a multi-core plus SIMD is actually architecturally similar to the GPU. So if you understand one side of that, you understand the other. But the cool thing is there are web technologies that are emerging for each one, and because we're using compilers, you might not have WebCL, but hopefully once we put in more backends for Superconductor, you'll have at least some combination of these, and so we'll be able to deploy on pretty much any browser. Except for IE 10 or below. So there might be a cloud solution in the future. If you're interested in that, come talk to me. And again, these are. I would actually think these are pretty low level. If you want to do communication, you have to use weird stuff like typed arrays, which brings us back to Fortran essentially. And so I claim that using DSLs to compile into these things is, if you really want to get good performance while not killing your weekends, that's the way you want to do it. And the final thing is, hopefully a blow your mind moment, is the way what I just showed you was actually a browser in a browser. It's kind of a meta thought where the browser has a parser, a selector engine, its own layout engine, its own rendering engine, and you feed a web page through that. What I just showed you was the exact same thing, but running in a JavaScript library. You take your data visualization, you run it through our JSON parser, and then actually instead of using the browser's slow native components, we run on the GPU for everything else. So just as we did tree traversals for layout, we do tree traversals for selectors on the GPU. And same thing for layout, and then we'll do the WebGL rendering. And so we do the entire animation loop with your favorite web languages plus our new attribute grammar stuff, and run all of that on the GPU. You never have to communicate with the CPU, and we kind of blow a normal browser out of the water. So hopefully that's exciting. And kind of going back to the beginning, now that we have this full automated process for doing layout, I'm hoping that we can, for example, do smarter debuggers than something, kind of these normal Firewall type of things where you just see what the current value is. And now we might be able to give you explanations, for example. Okay, let's do one final demo. So there's this cool video that GE put out where GE has a lot of time series data. Let me show you what that means. So time series data is essentially a fancy way of sending you up lots of time-up line graphs. And for example, let's say you have a bunch of servers giving performance data, so each line would be a server, and over time you're giving performance data for that server. So GE has this problem that they have lots of these things, and they have the questions like, for stocks or servers, how do we look at this? Like, I was looking at a demo today of actually a finance guy. He had like things like 1 million data points every millisecond. Like, so how do we deal? And that's right for one stock. So it's fun stuff. And so they came up, like, if you look at it all on the line graph, it looks like noise, right? But they came out with this cool concept of, well, let's make it 3D. So here we go. So now we actually, maybe we're looking over time. That's what this means, and we can start distinguishing them. And it's just like a proof of concept video. Like, let's experiment with it. But what I found interesting is they did it as a video. Like, I don't know what it took to make a video, and I don't know if they plan to make a video for every single stock, but like it's definitely the concept. So I spent about 1 weekend seeing if I could do it in Superconductor. Looks kind of similar, right? So here, for example, let's take a look at this let's look at this lump right here. So let's rotate it into view. All right, and then let's zoom in right here. So I'm actually showing you about 100,000 data points right now over maybe a couple hundred line time series graphs. So let's, to look over here, let's zoom in from the left. And I should point out I'm not a data visualization designer, so. And then let's zoom in from the right. And I don't know, random. Maybe we want to move a bit, look over time, just so instead of changing the time knob in the movie, let's actually really explore the data. So anyway, so this is just another attribute grammar. I think there's just a couple hundred lines of declarative code, and we did what kind of GD guys, I don't know how long it took them to do it, and did it in a non-interactive video. So I'm going to say thank you, and also we have a website at cu-lang.com. So we're slowly putting it up and trying to make it all accessible. But like this weekend, I put up a web service actually, so you can use our JavaScript backend and run today. We have a survey, so if anybody here does stuff with data sets, I'm actually curious to if this is kind of relevant to what you do. I'm trying to see if I can take this full time.
What is this organization? The website's for? Is it developers or?
Yeah, right now it's just like an open source project, but I'd like to take this full time somehow and see if maybe we could do something. This is how we have GitHub. We can keep doing this cool stuff, but then actually make a living out of it somehow. But yeah, so I'll be around near probably the beer. So thanks.
Thanks for everybody for coming. Again, stick around for half an hour, 45 minutes, have a beer. Everyone take a couple questions. If anything.
Oh, yeah.
Does anybody have questions?
Yeah. So I think you said most of what you're showing is CL. Sorry, but CL. What do any browsers actually support CL?
Yes and no. So it's Samsung and Nokia. We're building it because their mobile platforms needed it. Google, I claim, is breaking the "Don't Be Evil" policy by putting their own language rather than OpenCL. But basically, Firefox, Safari, the binaries are there. The closest thing is actually Rivertrail, which is something we might be able to target, which I think is already in the Firefox nightlies. And so WebCL is kind of, I'd say, another year before it's like everywhere. But like because we're using compilers, part of my hope is that, for example, we could use Asm.js and web workers, and that might give us some of these things.
Have you been following the Famous team? Is the technology you're using comparable to some of the tricks they're trying to pull off?
Oh, they're the CSS thing, right?
Yeah, they're basically reverse engineering the CSS system at a higher level.
Yeah, I was looking at that. Like, I haven't seen any videos where, so I showed an example, for example, the million node animation.
Mm-hmm.
Like, I've seen kind of small, kind of very beautiful demos, but I haven't seen them really to say anything about doing anything new with performance. So, I just don't know. They haven't said anything to my knowledge. Well, thank you.
Like I said, stick around, have a beer, chat with somebody.
Can we do 15 minutes of fame?
I'm sorry?
15 minutes of fame?
Yeah, I don't know what that is. We should do it though.
Yeah, usually